to the 8th and last section of Lecture 1, Organic Contaminants. We're still talking about partitioning. In this case, it's between the sorbed phase, or the solid material, and the water. We're going to assume again, as we have in the past, that this distribution occurs at equilibrium. The system is homogeneous, each phase is homogeneous. System's closed, there's no mass loss in the system. And what we're trying to do is develop very simple equilibrium approaches that will be useful for estimating or initially assessing the distribution of contaminants in the subsurface. So the coefficient we're after now is Kd, absorption coefficient. The idea that the subsurface is a slow-moving environment probably makes our equilibrium approach of some use anyway. It's really derived from work by Don Mackay and others presented in 1991. So, to estimate the partitioning of the chemical between the water and the solids, we have really two ways. The first is to do some measurements, do a lab experiment, to measure the concentration in the solution and the concentration that's sorbed, to directly measure Kd. We'd want to use site groundwater, site soil, and we vary the concentration in a variety of experiments. What we're trying to do is develop a plot of the sorbed concentration versus the aqueous concentration. We would take that data, and hopefully a linear straight line would fit the data fairly well. The slope of that line is then Kd for that chemical and for that soil groundwater system. Another way to arrive at Kd is to estimate it using a variety of estimators. We start by measuring the organic carbon content of the soil. Then we go to the literature and find a value for our chemical of octanol water partitioning coefficient, KOW. The advantage of this is that KOW is available for virtually every organic chemical. We would then use correlations that are developed in the literature to obtain something called KOC from KOW. KOC is the organic carbon keyed partitioning coefficient. We would then proceed to calculate Kd by the simple formula. Again, the advantage of this method is KOW is available. FOC is a measurable parameter, the fraction of organic carbon in the aquifer. However, the measurement is difficult and not terribly reliable unless it's done by specific, well-qualified laboratories. Another way of looking at this, if you have data on organic matter rather than organic carbon, the assumption that the organic matter is made up of 50% carbon is not a bad one. The distribution coefficient Kd, normally in experiments, is fit by something called the Freundlich isotherm. The isotherm can have three shapes. It can bend down, it can be a straight line, or it can bend up, depending on the nature of the absorption process. Our Kd is really only defined for a linear isotherm, but in numerical models we can actually handle different isotherm types. But we really want to stick at this stage with a linear model. Note that even the curved models 1 and 3 are linear for a considerable range. So as long as our interest is within those ranges, we probably can apply a linear model without a large uncertainty. So, besides doing experiments, we indicated we can do an estimation with literature values and a few little measurements. So let's have a look at that. Again, we said we wanted to use the octanol water partitioning coefficient because it's available for virtually all compounds. Essentially what we're trying to do is to relate this surrogate octanol water system to the real system that we're dealing with, that is the water organic carbon. Embedded in this is the assumption, which is valid for virtually all organic contaminants we're interested in, the assumption that the absorption is to organic matter in the soil, not to mineral matter or onto surfaces. What we need to do, of course, is then translate KOW into Kd. How do we do that? Well, again, we use the octanol water partitioning coefficient because it's tabulated. Some sources are listed here. Here are values of the octanol water partitioning coefficient, again, for the different classes that we've been discussing. And again, it ranges over orders of magnitude. Now remember, Kd isn't directly equal to octanol water, but it's proportional to. We can also estimate solubility from octanol water partitioning coefficient. So let's start that translation. We'll take a very simple form of a relationship that Don Mackay defined in 1991. It's not a bad approach. The organic carbon keyed partitioning coefficient, KOC, is equal to 0.41 times KOW. So this provides an easy way to calculate KOC for our organic contaminant, since we already have KOW from a tabulated value. We can then develop Kd as being equal to the fraction of organic carbon times 0.41 times KOW. And I warn you that this is a rough estimator of Kd. Experimental ways would probably be better, but again, we're here just after an estimation, not a detailed measurement. So how could we use this? Here's an illustration. We're wondering, in a soil that contains some benzene and some DDT, that is a milligram per kilogram of each in the soil, if there will be a groundwater issue from that soil, and which of those chemicals is more likely to cause a groundwater impact. Let's assume the soil contains 2% organic matter, and let's estimate the aqueous concentration in the water in that soil. So here's a number of steps that we need to undertake. First thing we want to do is convert FOC to 0.02. That is, to take the percent and convert it to a fraction. We then want to establish the value of FOC times 0.41 times KOW. Since we have KOW values, that's laid out here. We then calculate Kd. For benzene, it's close to 1.1. For DDT, it's 12,000. As you can see, DDT has a much higher KOW. That means it tends to absorb more strongly. So let's calculate the concentration that would be in water in equilibrium with that soil. So benzene would be 0.8 milligrams per liter, and DDT would be a very low concentration. Again, DDT would prefer to be in the adsorbed state as opposed to dissolved in water. Well, what do those numbers mean? Well, here's some typical drinking water standards. For benzene, 5 parts per billion, or 5 ppb, 5 micrograms per liter. And DDT is even lower concentration, 0.0028 milligrams per liter. Note, however, that for benzene, the water in our soil exceeds the drinking water standard. So benzene would be of some concern to us in a groundwater setting. DDT, on the other hand, is many orders of magnitude less than the action limit. So we're not too worried about DDT. It's one of the reasons I suggest that highly adsorbed organics are not only not terribly soluble from NAPL to water, but if they are in the water, they'll tend to partition onto the solids and really not migrate very quickly. So our concern for contaminants are really the mobile organics. Well, we used a very simple correlation between KOC and KOW. There are more detailed correlations available that are probably better for specific groups of chemicals. For instance, we might want to use equation 4.9 for aromatic hydrocarbons because it was a correlation developed using aromatic hydrocarbons. What's the penalty for using Don Mackay's very simple equation for every chemical? Well, we could illustrate it on this diagram. It's a plot of KOC versus octanol water partitioning coefficient, and it shows the various correlations from the previous slide, as well as Don Mackay's very simple line. you can see that in the middle of that diagram, the correlation isn't too bad, within an order of magnitude, let's say. When we get to the extremes, both for low KOC and high KOC, the correlations become poorer, the scatter of data is even greater, and Mackay's line is a poor estimator in many cases. That's really not a worry to us. Well, why is that? Well, here, the organic carbon key coefficient is too low. There's really no retardation at all. So whether or not it's none or virtually none doesn't really matter. Similarly, at the high end of the KOC, absorption is so strong, it really doesn't matter how strong it is. So contaminant hydrogeologists are focused more on chemicals in the intermediate area in terms of our need to determine the retardation or KD distribution coefficient, and therefore Mackay's value is probably not too bad as a first estimate. So when is this model reliable? We're really assuming that the organics are attracted to the organic matter in the soil. Well, that works well for hydrophobic organics because by nature they are attracted to organic matter. Like phases enjoy like phases. So the chemicals that this really applies best to are uncharged, so there's no ionic absorption, and hydrophobic. And one way to define hydrophobicity is through the KOW value, and I would say a KOW value above 100 is hydrophobic. The other requirement is that all concentrations be low, all organic concentrations be low. We don't want interferences between the organics as they try to absorb. The geological material has to have some organic matter. The FOC really should be above 0.001. It might be lower if the organic contaminant is extremely hydrophobic, but that's a good rule of thumb, I think. We can refine the model, and it has been refined remarkably over the last 15 years. A good paper to look at for significant refinements is this one. As we'll point out later in the course, the value of KOW, in fact, is not precisely known. If you look in the literature, you'll find a range of values that different people have provided. So it'd always be better to get a more true value of KOW. Measuring FOC is painful. If we're using solubility to calculate KD instead of using KOW, then solubility data should be improved as well. And again, we should perhaps restrict our use of the correlation of KOC, KOW to similar compounds where a correlation has been well established. Well, that's the end of partitioning. We've discussed the importance of phases in the subsurface. There's 4 phases. We identified that solubility is the partitioning between the NAPL and the water, and it's well described by Raoult's law. Vapor pressure, the partitioning between the NAPL and the vapor, is also described well by Raoult's law. Water vapor partitioning requires Henry's law constant to be determined, and the absorbed aqueous partitioning is defined through the KD approach. We've also finished Lecture 1. What were the highlights? Well, we've welcomed you and we wish you good luck in the course. Hope you enjoy yourself and are successful. We've identified to you that most organic contaminants are quite simple organic molecules, and that's really good for hydrogeologists. We suggested that we can look at the subsurface as really 4 compartments: the non-aqueous phase liquid, water, vapor, and the absorbed material. We briefly introduced remedial concepts, and I hope you take away the idea that we'll be able to succeed to completely remediate sites only rarely. And our objectives really need to recognize what is possible with our technologies and our experiences to date. And I hope I've convinced you that these simple views of partitioning between phases can be of some use as we approach many of these problems. So thank you very much for your attention, and we'll be on to lecture 2 next week.